All right, recording is rolling. It is Friday, September 16th. So we're having another one of these rainy type days where there's been a test in my room all day. Now, um, if you are in one of my relocated classes, you guys received some things from your covering teachers. Probably one of these flipbooks, so you guys could do a flipbook animation, apply some creativity and physics knowledge of kinematic, and also one of these analog calculator templates. And you guys in my class right in front of me right now have one of these templates, which also includes a paperclip. Right, so we're about to get to that. Oh yeah, you guys probably saw here just yeah, it's just for the record for completion. That's where some relocations that happened today. I posted this to Classroom yesterday afternoon. So I got that. All right. Yeah. So we're gonna have to delay all those forces and dynamics labs and demos and the whole deal until Monday. But you guys know that. But my AP students in particular, I'm just making one all video. Go ahead and read ahead, take a look at the resources. There's some good resources on Google Classroom. Don't forget also those AP videos on AP Classroom. So take a look at that's just for my AP students. So you guys get that. All right, but let's dive into this analog calculator. So I have a few rainy day activities lined up, and today's a good day for one of these. All right, so yeah, let's go back to let's time travel in our minds back to the 1970s. That's I think the last time we had a manned mission to the moon was 1972. I want to say. Okay. And suppose you're a NASA scientist or engineer on the team, getting astronauts to the moon and back. Do you have one of these nice scientific calculators in your pocket? No. What did calculators look like in 1970s? Say 1972. Yeah. It's like a big old computer, like the size of this room, right? In fact, this probably is like more calculating power than what they had in the Apollo missions. So, what were they doing to make? I mean, they were probably doing all kinds of calculations. What were they actually using? You guys ever heard of something called a slide rule? A slide rule, right? Okay. Well, we're going to do a version of a slide rule today. We're going to do a modified version that is actually circular. I really like this model. So you guys have one of these templates on your desk. Go ahead and just follow along with me. Cut out this template. We're going to cut out both circles, and then I will tell you guys what this is, how to use it, and then yeah, just for context, yeah, back in the 1970s when they were go back to the 60s even when they were launching all those Apollo missions, they were using just a linear version of this. So it was like this, but linear. Okay. So you guys kind of learn a little bit about slide rules, just a circular version. Okay. While I'm cutting this out, I'll tell you guys a little bit of background where I got this from. There's a YouTube channel called Mathologer where he covers this. So I took some screenshots, cleaned them up a little bit, and painted PowerPoint, and here it is. Here we have it. So that's actually where this comes from. Okay. So it's off the YouTube channel. Bam, got that. All right, you guys are cutting out yours as I'm cutting out mine. A couple of circles. Even as you guys are cutting this out, even before you cut out, you guys can see the numbers going around the circumference are not evenly spaced. See how they're not linearly spaced? Right? Like between the 1 and the 2, there's a huge gap. Between the 2 and 3, it's a little bit smaller. And then between each pair of successive numbers, it gets smaller and smaller and smaller until like 7 to 8, 8 to 9. Ooh, it's a little tiny gap. Okay. And then notice that there's no 0 and there's no 10. It goes 9, 9.5, and then it goes back to 1. Huh. So that's kind of interesting. I wonder what that's about. We're about to find out. Okay. So actually, speaking of those number spacings, like what's the deal with those number spacings? Let me give you guys a couple of perspectives, because I mean, if you don't know, then it's like, well, what the heck? Why are they not evenly spaced? What's the deal? Right. So these are actually logarithmically spaced. You guys know about logarithms, exponents, right? So that has to do with the spacings. You guys will see the connection as I have you guys do some calculations for these, right? And what I saw in the video where I grabbed this template from was supposedly this would be true. So say you take a rubber band. Can you guys imagine like a rubber band? And you actually do have it evenly spaced. Oh, I can kind of use my ruler right here as an example. Okay. And you number it say like 1 through 10, right? Well, yeah, let's go 1 through 10, right? And then you take the 1 and you attach it right here, right where that 1 is. Actually, I think it should go. Try to remember how this works now. Should go here. Do the upside down version of this. Well, be kind of backwards, I guess. Right? Right. And then I start to. Oh yeah. No, we're good. We're good. It is like this. Right. Then I start to wind this around. Right. So now remember I said this would be like a rubber band. It's numbered 1 through 10. I'm going to take the far end over here and like attach it to a wall, so that, and then this end will be attached to the number 1, so that as I start to rotate this, it's going to stretch the rubber band. Right? You guys get that? Right. So this rubber band is number 1 through 10. It's like being stretched as this is going around. Right. So going from the 1 to the 9, it doesn't stretch very much, and then 9 to the 8, ooh, it stretches a little more, and then the 8 to 7 stretches a little bit more. Right. And then you do this all the way around. And then by the time you close it, to go from this 2 to this 1, doesn't have to stretch that band a whole lot. Ooh, that's a huge gap. Okay, you guys see that? Okay. Now, why does that space it logarithmically? I don't know. I can't independently verify that. I've just been told that that's true. So, hey, got that off the internet where everything else is true. So yeah, let's run with that. I guess it's sort of believable, right? Whether that's an approximation or exactly true. Yeah. Huh. So, all right, you guys up to where I am right now? You guys got these? Okay, yeah. Looking around the room, looks like everybody's got these 2 cut out. All right. So next thing, you guys see a little hole right in the middle? All right. So take either the paper clip on your desk or a pencil or a pen and punch a little hole right where that is. Like, bam. And the other one. Bam. Right in the middle. Okay, so you guys got holes right in the middle. Okay, you guys got that? Oh. All right, so everybody's up to this step. All right, now paperclip time. Paperclip we're just going to use to hold everything together. I guess you could use any kind of axis. So we're going to use this as an axis here. Okay. So take this, push this through, right here. And bam. All right. You guys see how you can like rotate this? You guys see that? It like rotates, right? Okay. Let me give you guys a moment to get to where I am. You guys should be able to do this just like I'm doing it. Okay.
I know. I'm aware. Oh, can you show me how to do it?
Oh, paperclip? Okay. Oh yeah. Why don't you see it once, right?
Oh, you didn't know.
Okay. So remember, you go like punch, punch. Got a couple holes right in the middle, right? This right on top of this. Okay. Take the paperclip, feed it through. You might have to warp the paperclip a little bit. You can just warp it back later, right? It might make it easier to push that through there, and then push it through right here, right? Right. So it flips everything together. Okay. Then just rotate it around a little bit and tuck it right in there. Okay. On the other side, maybe I'll want to work this back. I don't know. I guess you don't have to, but good, right? All right. All right. So it's like kind of like rotate around, right? All right. Okay, so looking around the room, I think everybody's up to where I am now. Right. Almost. Okay. All right. All right. So you guys ready for the next step? All right now. Do you guys see how you can actually align each number, inside number, to each outside number? Right. So the inside yellow and the outside is white. Like this 3 and the 3, that's aligned. And when you align those two, the 4 and the 4, the 5 and the 5, 6 and 6, 7 and 7, all the way around, they all align, right? Except, and this particular wheel, it's scaled according to the base 10 system, since we have a base 10 system. right? So it goes 9, 9.5, and then 1. That 1 could really represent 1 or 10 or 100 or 1,000, right? You guys see this is going to involve like a floating decimal and point system, right? Same thing was true back with the slide rules back in the Apollo system. When they would use slide rules back in the day, they had to, we're about to do some multiplication, division, and also square roots with this, right? They had to have a good idea just in their own minds, like where the decimal place would be, because there's like a floating decimal point. Okay? And you guys about to see that, right? So here's what we do now, right? So everything's aligned. All the inside numbers and outside numbers are aligned. Now we're going to change that. I'm going to rotate this inside yellow circle. Let's rotate it so that the 1 matches with the 3, just for an example. Okay? You guys see the inside 1 matches with the outside 3? You guys see that? Okay. And you guys have the same on yours? Right. Now, hold those in place relative to each other. Do you guys see that the 6 is aligned with the 2? And the 9, the outside 9 is aligned with the inside 3? You guys see that? Right. Hey, what if you sort of treated these like fractions, like ratios, like a 3-to-1 ratio? Well, that's obviously 3-to-1. That's already reduced. But what about 6-to-2? Hey, 6 over 2. Is that also a 3-to-1 ratio? Let's rotate a little more. What about 9/3? That's also a 3-to-1 ratio, isn't it? Right. Let's check some other ones. Oh, what about this? Look, 1.2/4. Is that a 3-to-1 ratio?
Yeah.
It is if you allow a floating place decimal, right? Floating decimal place, because that could be 12/4, couldn't it? Right. So if you see 1.2, that might actually represent 12 or 120, right? You can use your imagination, right? Allow the decimal point to float. Let's do one more. How about 1.5/5? Well, it could be 15/5, which would also be a 3-to-1 ratio, right? And you know what? I picked 3 and 1 just randomly, but you could pick any pair of numbers. Here, let's say take the 1 and align it with the 5, just to show you guys a second example, just randomly, right? 5-to-1. Hey, 1/2. That could be 10/2, which is a 5-to-1 ratio. 1/2 is 0.5. 1.5/3. That could be 15/3, right? Yeah. So no matter how you rotate the yellow circle compared to the white circle, the inside to the outside, the pairs of numbers outside inside will always be the same ratio, right? Now we're about to take advantage of that property to do some multiplication and division. Let me go back to what I had before. Let me align the inside 1 to the outside 3. Okay, so I have 3-to-1 ratios. You guys see that? Okay. Now if that's true, if I have a 3-to-1 ratio all the way around the circle, okay, let's set this up. Here, 3/1, because that's that right there. Let me say is equal to, and then just rotate this a bit. I'm just gonna pick let's say this example, 9/3. No, scratch that. Let's do 6/2, just so all the digits are different. 6/2. Right. That would be true, right? Right. And I could pick any pair of numbers, 360 degrees all the way around. I could pick any pair of numbers. So I just pick those two, and they would equate. Those ratios would equate. Right. Now, if that's true, like 3/1 is equal to 6/2, if those ratios are the same, right? Do you guys remember like cross multiplication and division, right? So here, how about this? If the inside number, if you always choose the yellow one, right, the one on the inside circle, which is on the yellow circle, right? Do you guys see that will already solve any division problem that you can ask for, right? So I wonder what 6/2 is. Well, it's just whatever number the 1 is pointing at, right? You guys get that, right? So you could do anything crazy. Let me do some crazy divisions. Let's say I point the 1. I don't know. Let's just roulette this thing. Just okay. It's just random spin. I have no idea what's pointing at 1 right now. What's pointing at what? So we'll spin here. All right. So let's say I want to know what is 88/42, right? 88/42. I wonder what that's equal to, right? So on the outside, I can say find 8.8. That's about right here-ish. And the inside, I can find 4.2. That's right about here-ish. And I can align those two. 8.8 is right there. 4.2 is right there. Bam! I have an alignment, right? So this would represent that ratio. And then I can rotate my circle, and actually they're locked in place relative to each other, and say, where's the 1 pointing? The 1's pointing just a little bit more than the 2. It looks like about, it's really close to 2.1, right? So that means that the answer would be really close to 2.1. Let's see if that is. 2.095. That is extremely close to 2.1, isn't it? You guys see that? Right? So, yeah, so you can do divisions really fast, but you can also do multiplications really fast too. You guys remember cross multiplication? Right? Like, here, how about this? I can take this 2 multiplied by this 3. That's equal to 1 times 6. So here's what cross multiplication says. 3 times 2 is equal to 1 times 6. Isn't that true? Right? And if that's true, then again, you can use this 1 sort of as a pointer, like an arrow pointer, and point it to any number. And these two numbers multiplied together are equal to this number on the outside. You guys see that? Right? So these two multiplied is always equal to this number on the outside if you're using 1 as a reference number. Right? So let's try crazy multiplication. Let's do hey, let's go back to the same numbers I chose before, except I'm going to say times, because got some random numbers. 88. I wonder what 88 times 42 is. 88 times 42. Right? Now, here, let's do the same thing. So if I want 88 and 42, I got to have an outside 88, and the 1 is pointing to that. So I'm going to take the inside 1 and point it to 88, which is right, bam, right there. Right. So that 1 is pointing to, well, it says 8.8, but we're going to allow the decimal place to float. Right. Okay. And then multiplied by, what do you say, 42? Right. So 42 goes where that 2 is. So that's the yellow inside circle. So 42 is bam, right there. And it looks like it's pointing to, it's really close to 3.7. To 2 digits is 3.7. It's kind of hard to tell from there, but it's 3.7 something. So let me write down to the digits 3.7. So what is 88 times 42? Right? It's really close to something to do with the 3.7. Now, the last thing we have to do is restore the decimal place. So, guys, 88, is that pretty close to 100? That's a little less than 100, right? Right. If I multiplied 42 times 100, that would be 4,200. So since 88 is a little bit less than 100, the number should be a little bit less than 4,200. So this is 3.7, what? How many zeros should I put? 3.7, what? How about 3,700, right? Right? Should be pretty close to that. Now let's verify. I haven't done this ahead of time, so I don't know, but we're gonna see how close this is. What is 88 times 42? It's 3696. It's exactly equal to 3696. Wow, look at that. It's so close, so close. And I got that just using the analog calculator, right? So what you lose with slide rules and in this case, a circular version of that is like exact precision, right? But it nails it so close. You guys see how close that is? Right, pick some random numbers, right? You guys good so far? Right. One last cool trick I wanted to show you that you can do with this. And actually for this last trick, you don't even need both circles. You just need one of the circles. So just to really emphasize that point, I'm going to take this apart and just focus on one of these. Okay? And that's how to do roots, square roots, cube roots. I'll show you guys how you can do square roots and cube roots. And again, you only need one of the circles to do that. Okay? Guys, how about this? What is the square root of 10? Does anybody know? Square root of 10? Okay. How about this? Since we're dealing with something that's like logarithmic or exponential, can you rewrite square root of 10 in terms of powers? Who remembers what the square root of 10 is in terms of powers? That's 10 to the power of what? 1/2. Yeah. You guys remember it's 10 to the power of 1/2? Okay. All right. So how is that going to help us figure it out using this log scale circle? Well, find the number 10, which is actually the number 1, isn't it? Right? Right. And between the number 10 and the number 1 is the placeholder, which happens to be itself in this case. Maybe I should pick a different one, but we'll do some other examples. Right? Find what's halfway around the circle, because the power is 1/2. Right? All these numbers are like scaled according to power because it's logarithmic, right? So what's exactly halfway around the circle? And I could even use a ruler to get it exactly halfway around the circle from the 1. The 1 and the 10 is the same number on the circle, right? It looks like it's 3.1 something. It's between 3.1 and 3.2, right? It's between 3.1 and 3.2. Okay, that's exactly on the other side of the circle. Let's see what is the square root of 10. Hey, it's 3.16. Look at that. Look at that. right? So you can take a square root using just the circle. You guys see that? Well, let's do another square root. Let's do the square root of, how about 73? I don't know, square root of 73. Right? I wonder what that is. Right? So on the circle, I need to find 73. Hey, there's a 7.3. There's sort of that, right? That's like right 70. It's right about here, right? So what's halfway between that and this one? Between these two, right here, between here and here, what's halfway? Okay. Well, let's see. It's probably gonna kind of estimate. It looks about here-ish. I think this is halfway between here and here, right? If I'm working around from here to here, so right about down here, and it says, but I'm gonna guess it's about 2.6 maybe. 2.6. Right. Let's see, what is the square root of 73 exactly? Square root of 73. Okay. No, I know what's going on. Here, watch this. The square root of 7.3 is in fact 2.7. The square root of 730 is 27. Right. But if you have the square root of 73, yes, sometimes you have to do it the other way. So what's halfway between here and here? Right, between this 73 and this one. Well, in this case, it looks like it's about 8 point something. So let's go. The square root of 73 itself is 8.5. 8.5. Yeah, so it does work. Now, whether you work your way around halfway around this way or halfway around this way, there's probably some rule for it if you get really comfortable using a slide rule or this calculator. But in this case, we had to go halfway between these two. Right here, you know what this is kind of related to? Here, this is 8.54. Right. I know an idea that this is related to that's kind of good to know before you graduate high school. Let's do a bunch of square roots and look for a pattern. Square root of 1, square root of 10, square root of 100, square root of 1,000. Let's do 2 more. 10,000, 100,000. Okay. I wonder what each of these numbers is equal to. Okay. Well, guys, square root of 1, what's that? 1. What's square root of 10? Well, we just did. Really close, really close. Yeah, really close. It actually is really close to pi, isn't it? Square root of 100. Square root 100. 10. Yeah. Square root of 1,000 is 31.6. Huh. How about square root of 10,000? 100. It is 100. Square root of 100,000? 316. Yeah. All right, you guys. Let's do one more after this. A million. Let's do an even million. Should be 1,000, right? Yeah, it's an even 1,000. Right, do you guys see a pattern? See how it like oscillates back and forth between like the even powers versus the odd powers, right? You guys see that? Right. So the fact that there's like a 2-track, right, evens or odds, that probably has something to do with whether you go like halfway on one side of the circle or halfway on the other side. They can still do square roots, right? Hey, I wonder if you could do cube roots. Cube roots. I wonder what the cube root of. Let's do one that we all know. Guys, what's the cube root of 8? 2. Yeah, you guys are saying 2 because 2 times 2 times 2 is 8. So the cube root of 8 would be 2. Right? You guys, is that the same thing as 8 to the power of what? A third, right? Okay, so if I find my 8 and I find my 1, and I go a third of the way between those two, but let's say I go around this way around the circle, right? This way around the circle, a third of the way. What's a third of the way? Well, if I could kind of split this up into 3 parts, like part 1, part 2, part 3, right? You guys see that? Right? Here's a third of the way right here. You guys see it? It's exactly a 2. It's exactly a 2, isn't it? Right. Hey, what is how about 8 to the 2/3 power? 8 to the 2/3. 8 to the 2/3 power. I wonder what that is. Oh, is that the same thing as 8 to the 3rd squared? Is that the same thing? Right? That's the same thing, isn't it? Right? And you guys know what 8 to the 3rd is. We just did it. It's equal to 2. Right? So, guys, what's 2 squared? 4. Right? Wouldn't this be 4? Right? And on the circle calculator, that'd be 2/3 of the way between the 1 and the 8. So 1 is my like home base. Right, 8's here. All right, here's my thirds where my thumbs are. Right, a third of the way is right here, which we just did. That's equal to 2. Right, what's 2/3 of the way? That's my left thumb. Oh, that's exactly on the 4. Look at that. It is 4. All right, so now you can do all kinds of crazy roots and powers with just a single circle. Okay. And again, if you combine those circles and throw a paperclip in the middle and start rotating them, you can multiply or divide any numbers you want. Just remember, you have to float the decimal place, so you have to also keep track of, well, where would be a reasonable place for the decimal place. Okay. All right. All right. So I hope you guys enjoyed that. Let me just clip this back together for final shot on this video. All right. So fun times with multiplication, division, and roots on a circle calculator. All right, and that is a wrap on today's lesson. Rainy day. All right, you guys have a great weekend.